Those of you who have attended the previous years will know that we like to start things off by stretching our minds a little, by looking at things from a different perspective, a different angle. This year, we are going to take a high-level view. And by high level, I mean from outer space. It is an honor to welcome our first guest, Berkeley Professor of Astrophysics, Chung-Pei Ma, who will elaborate on the surprising link between art and science.
Thank you very much, Delia, for the invitation to participate in this event. I do astrophysics as a living, and I study among astrophysics disciplines. I focus on the largest scales, meaning cosmology. So I study galaxies, very, very big black holes, and the past, present, and the future of the universe. And I just came off from a 3-day conference at Berkeley celebrating the 80th birthday of a famous colleague of mine who is a theoretical astrophysicist. And it was held in one of these physics auditorium, nothing to compare to this beautiful venue. And we had 3 very nerdy days of equations and discussions. So it's super refreshing for me to come out to San Francisco today now and to just share a few thoughts with you. I don't usually talk about art and science, but Delia gave me this very exciting, stimulating topic. So I just have a few very thoughts to share with. Okay. So just to start with, this slide is actually a combination of real astronomical images and artist's rendition. And this was made about 10 years ago when my team discovered the largest black hole in the universe. And so we had to do a press release. And this is help with the National Science Foundation and the Gemini Observatory and the NASA, in which you are seeing actual images. On the upper left is the galaxy we looked at. That's at many, many millions of light years away. And then we zoom into the center. So this middle image, you are seeing actual stars taken by Hubble Space Telescope. But this dark ring you're seeing here illustrates the black hole. It's not a direct image. But we wanted to, the way we infer this black hole is to use the motion of luminous stuff we can see that's orbiting around the black hole, i.e. the stars you're seeing here, to infer the dark thing. That's sort of the theme of my research, is I use luminous things in the universe to infer the dark side of the universe. And the universe is mostly made of dark stuff, actually. Okay, and then the illustration, the lower right is meant to illustrate the size of this black hole, the event horizon, the size, the boundary of no return. So if you were to fall into that sphere, indicated here by a circle in projection, even light cannot escape, hence a black hole is black. So don't get close to that. But the illustration is to show that the size of this black hole, which has a mass of about 10 billion that of the sun, 10 billion times the mass of the sun, the size of the event horizon is a bit bigger than the solar system, as you see here. Okay. After Delia contacted me, I thought maybe I'll talk just very briefly about some thoughts about the science of art and the art of science. Okay. So when I thought about science of art, I thought about this fluid dynamics class I teach to our physics graduate students at UC Berkeley. And this is one example I use. So here you're seeing an artist actually practicing fluid dynamics. And Jackson Pollock, of course, is well known for his drip painting. And here's a scientist view of fluid dynamics. No worries, I won't go into the equations, but fluid dynamics is a bread and butter piece of physics that had been developed for over more than 100 years. And so as part of this graduate class, I asked the students to do a little research and do a presentation in class at the end of the semester. So one year, one of the students chose not climate modeling, not supernova explosion, astrophysics, fluid dynamics, but he chose to study the fluid dynamics of Jackson Pollock's drip painting. And I knew nothing about that, so I was really impressed when he did the presentation and then showing that, in fact, there have been scientists studying the technique he used to generate these famous paintings. And one key thing people highlighted was that, of course, probably we didn't think Pollock knew about the instability of viscous fluid, but we know that he practiced a lot the speed of which he moved his brush and the height from the painting. And there have been a lot of videos. So these scientists analyzed these things and then noticed that he had his speed of his brush, he practiced so that it's fast enough so he could avoid some of the so-called coiling instability that will get the paint kind of smeared into these coils. But if you zoom into some of the little corners, you can see the coiling if you don't move your brush fast enough. It also depends on the viscosity of the paint. Okay, and this is actual equations showing that what you need to do to balance hand is the speed of the hand. That little Greek symbol there is viscosity and gravity and so on to explain how he generated these beautiful art. Okay, just a very quick thought about the science of art. So how about art of science? So another very, very beloved painting, of course, is this one. And this was actually taken from my iPhone when I was in the New York MoMA. I was amazed by how close they allowed us to walk towards this painting, unlike Mona Lisa in the Louvre, which, as you know, you can barely see it. And this beautiful painting, as you well know, has starry nights there that are blurred. And the blurry of the stars, shown here, they are actually the enemies of astronomers. They are due to atmospheric turbulences, right? We sing, "Twinkle, twinkle, little star." Have you ever thought about why stars twinkle? It's the atmosphere's turbulence. And that really smears up the images for us. So that's why we go to space with Hubble Space Telescope or James Webb Telescope. And from the ground, it limits our resolution. Okay? But in this picture on the right is an actual photograph of these so-called billow clouds. So some people think perhaps Van Gogh those swirls may have been the billow clouds. And billow clouds actually are one example I use, again, in this fluid dynamics class, and you probably can't see anything here, but don't worry. This is actually my own boardwalk, deriving the so-called Kelvin-Helmholtz instability, okay, and shown here in that red equation, it's trying to explain the billow clouds. That would be one application. And the formation of these beautiful clouds is usually caused when you're fairly close to a body of water. So you got air, one layer of air, and you have a bottom layer of air that's more moist. So it has a little bit higher density due to water. And then when you have these shearing velocity, when the two layers of air move relative to each other, and when the lower one is just slightly denser than the upper one, you get these Kelvin-Helmholtz instabilities causing these beautiful clouds. Okay, so it's another example of the nature's working and perhaps showing up in art. Just one other example is Da Vinci's attempt to draw turbulence. He was fascinated by these turbulent motions, okay? And on the left, you're seeing the eddies. And in fact, he was the one who, this is in the 1500s, that he noticed that running water will show up at these eddies. And now we know there are effects of turbulences. Okay? And turbulence is one thing that we physicists have a lot of trouble understanding, in the sense that we know it when we see it. We all know turbulence when we're flying. But it's so chaotic and nonlinear, the phenomenon. Even till today, we don't have a very detailed mathematics to describe the motion of turbulent flows. But we have sort of statistical understanding of it using the concept of eddies. So you have sort of a mean motion, and then you have these swirls, whirlpools, going around that. And that's actually what Da Vinci already realized when he drew this painting. Okay. So just very last thing I want to share now here is a scientist image of a black hole. Some of you may have seen when the Event Horizon Telescope released this image, a beautiful image a few years ago. But I want to also talk about artists' view of a black hole. And I had the privilege a few years ago to join this project with New York-based artist Amanda Bakia, and sponsored by the Heising Simons Foundation. So she had this project of going around different cities in the United States, drawing murals on some public walls she was able to get hold of, and depicting people doing science. So she contacted me wanting to do a mural of black hole, featuring sort of my research. So I actually worked with her on her design, and on June 30th in 2021, we showed up in San Carlo, which is some of you must have been there, is right next to Redwood City. And you can see the lower image here, it's by a crepe store. It's in downtown San Carlo. In this parking lot, she found this beautiful wall, and we had that public painting day. So she marked out what colors should go into it. You can see the community, especially little kids, they all showed up on Saturday. And I requested that I wanted to paint the black hole in the center here. And I was really pleased that that's about as close I can get to a black hole. Okay. So yeah, just to end, science plus art. Good things always come out of that. In this case, it would be donuts. Okay, so thank you very much.